So, hello friends, today's lecture will be on high temperature deformation and that is called in a word creep behavior, and this type of deformation takes place for any material which is exposed to very high temperature and under certain load conditions, and then it will keep on deforming as a function of time. So, if you see the creep application, that the understanding of creep is required. So, it can cover a very large size scale. For example, it can be important for a electronic circuit where because of the flow of the current all the components are exposed, get slowly heated up, and with the time, okay, all these soldered joints and the wherever there is a connection between the circuit and some component, these are exposed to high temperature. So, it will keep on experiencing some strain as a function of time, and slowly at some point of time it will fracture and your component will fail. So, it is important in a electronic circuit. Similarly, it is important in, for example, a gas turbine engine, okay, or a steam turbine which is used for in power plants, or a gas turbine which is used in an aeroplane. And these material, as you can understand, are exposed to high temperature. Okay, now we are all thinking about having ultra supercritical power plants. So, the temperatures are going to be very close to 650 degrees Celsius or 700 degrees Celsius. So, these material are exposed to very high temperature, and as you can understand, the turbines rotate at very high RPM, and so there will be large centrifugal force acting on the rotating parts. So, under high temperature, under this loading condition, the materials deform. Okay. So, it is a very important area of material science to understand that how the creep takes place and how you can design the material to reduce this deformation at high temperature. So, creep, if you want to define, it is a material subjected to a constant load at an elevated temperature. So, elevated temperature also has to have a definition, that what do we mean by elevated temperature. So, elevated temperature is around any temperature above 0.4 or 0.5 of the melting point of that material. Okay. So, under a constant load at these temperatures, a material usually show deformation. Okay. So, it shows a time dependent deformation. Okay. So, as a function of time, the material will deform. So, at high temperature, other metallurgical changes which usually occur, we already know that equilibrium vacancy concentration will increase as a function of temperature. Some additional slip system become active. Okay. This we have not discussed, but usually we say that the close spec planes and close spec directions are the preferred slip system for deformation. But at high temperature, additional slip system can be active. For example, in HCP case, other than basal plane, which is the close spec plane and the direction in the basal plane, you will also have slip process in the prismatic or pyramidal plane, okay, depending upon their C by A ratio of that particular material. And then grain boundaries start taking part in deformation. Okay. This is a very important deformation mechanism which starts operating at high temperature. So, at high temperature, it is not necessarily that you will have only deformation through dislocation movement through the grain, but the deformation can be through grain boundary sliding, okay, which is what we call as that grain boundaries start taking part in deformation, and the process is called grain boundary sliding. Okay. In short, we also say GBS. So, instead of deformation through the dislocation within the grain boundary itself start deforming, okay, and kind of slide, one grain slide with respect to the another one. Other metallurgical changes which take place may occur, that you will have recrystallization process at high temperature. Okay. Precipitate growth will always take place at high temperature. You will have more diffusion of atoms, solute atoms. So, precipitate growth takes place. So, whatever you have planned, that these should be the size of the precipitate, this should be the inter particle spacing. Okay. But at high temperature, it will try to have a larger particle with a smaller surface area. Okay. So, at a high temperature, because diffusion is easy, so a small particle will shrink and the big particle will grow. Okay. And slowly you will have precipitate growth, or it can have oxidation problem. So, at high temperature, most of the material are susceptible to get oxidized. Okay. Because you always have a oxygen environment around it. So, at high temperature, the material start getting oxidized. Okay. So, oxidation is one of the big problem, corrosion problem for high temperature materials. Now, creep can be divided into 3 stages. Okay. So, if you see a strain here, the strain is shown on y axis, time is shown on x axis. Okay. So, as soon as some load is applied, you will have some deformation in the material. Okay. At 0 time, and then you will see that the strain is or what you can say here, the slope between strain and time is coming down as a function of time. Then it is showing what we call as a steady state behavior, that is the second stage. So, the strain vary as a function of time in a linear manner, and then you have the transient condition, again another transient condition, that is called the tertiary stage, the third stage. Okay. And in this case, the strain varies as a function of time. So, the strain accelerates as a function of time. So, if you see the slope here, the slope is continuously increasing, and then you will have fracture. If I increase the stress or temperature, okay, in both the cases, the whole of this deformation mechanism will shift to higher strain. So, if I increase the stress on the system or increase the temperature of the system, now you will have more strain at 0 time, and then you can see that the slope of this linear curve is also more than the previous one. So, steady state creep will also be higher. Okay. And the material will fracture at much lower time duration. Okay. At a shorter duration, it will fail. Okay. So, if material is exposed to high temperature or it is under higher load, okay, the material will fracture at a lower time. Okay. So, these 3 stages are given here. First is transient or primary creep, the strain rate decreases with time and strain. Okay. So, strain rate is decreasing here, you can see the slope is decreasing as a function of time. Second stage is secondary or steady state creep. Okay. This is one which actually you try to understand in more detail. Strain hardening is balanced by softening processes. So, here both the hardening and softening processes are balanced. So, hardening process is dislocation generation and they interact with each other. So, that is called strain hardening. Softening processes are, for example, dislocation get recovered. So, you again reduce the dislocation density, okay, and material becomes soft. So, the generation of dislocation and recovery of dislocation both are kind of balanced in this particular regime, okay, and that is why you get this linear behavior. In tertiary creep, the creep rate again accelerated at the last stage. Okay. This is due to because of the deformation, the whatever part is there, the cross sectional area is continuously reducing. So, it will reach a stage where now it cannot be able to take that load anymore. Okay. So, then there will be a very fast reduction in the area as a function of time. So, instability will be there and your creep rate will increase. Okay. So, the strain time curve can also be shown as the strain rate time curve. Okay. So, strain rate is nothing but the change in strain as a function of time, okay, d epsilon by dt. So, that also we can plot. So, you can see that in the first stage the strain rate is decreasing because here the slope was decreasing, and in the second case the slope was constant. So, strain rate is constant in the second stage, and in the third stage the strain rate is increasing. Okay. Again you can see the effect of stress and temperature. So, at lower stress and temperature the strain rates will be lower, at high stress and temperature the strain rate will be higher, and the time to rupture will also be smaller. Now, what is the difference between a constant load and constant stress creep data? Okay. In creep actually we have a constant load. So, you can understand that the stress is continuously increasing on the material because the cross sectional area is continuously reducing. As the length increases of the sample, okay, the cross sectional area will reduce. So, continuously for a constant load the stress on the system is continuously increasing. So, you can do test in two ways, either you do it as a constant load, then you get this typical curve, S shaped curve, okay, which we have just discussed in the previous slide. If you do it on a constant stress, then you do not get this tertiary stage, because this tertiary stress is due to the reason of reduction in cross sectional area. So, for a constant load the stress on the system will increase, but if you are maintaining the constant stress condition, that means you are taking care of the reduction in the area. Okay. So, you are reducing the load also on the system as your cross sectional area is becoming smaller and smaller. So, that is why for a constant stress you will not get this tertiary stage, the second stage will keep continuing, because I will keep reducing the load to maintain the constant stress on the system. In the stage second, these two will more or less will be equal. Only when the tertiary stage starts, when the cross sectional area is very small, which will not be able to take that constant load, and suddenly you will see the rise in the stress and rise in the strain rate basically. So, for a constant stress it will be same linear curve will be extending, okay, without any tertiary stage, and ultimately it will fracture. So, as I told you, this stage second is of importance to us, because that is the stage which covers the longest time in the creep curve, okay, and the material will undergoes this second stage for the longest time. Okay. So, we want to understand and we want to kind of characterize or quantify that particular stage, okay, to understand the creep phenomena. So, the steady state creep rate can be given by an equation like this, okay, epsilon dot second or epsilon dot SS, that is steady state here, a sigma to the power m prime, okay, exponential minus q c by RT. So, m is your exponent here, because these are as a function of stress the strain rate will change, okay, and it follows some kind of exponential behavior. So, a and m prime are the material constant here, okay. So, I will see constants. QC is the activation energy for creep, okay, and both these can vary with stress and temperature. For temperatures more than 0.5 of melting point, okay, that is where we do the creep kind of test, QC is equal to the activation energy of self diffusion. Okay. So, the activation energy of creep is related with the self diffusion of atoms. Okay. So, please recall what we discussed during diffusion. So, creep is intimately related with the self diffusion of atoms. Okay. Now, the creep mechanisms depend on deformation conditions. Okay. So, temperature and applied stress, for example, these two already we have seen that how they increase the creep rate, and they also in turn decide what will be the deformation process. So, depending upon temperature and applied stress, we will see that there are different deformation mechanisms which are operating. Okay. So, whether the creep is dominated by dislocation glide, okay, or it is dominated by dislocation climb process, or it is dominated by diffusional flow, that is decided by that what is your deformation conditions. Okay. So, if you look at the dislocation glide process, Okay. So, this is acting at low temperatures and high stresses. Okay. So, low temperature high stresses, it is like our normal deformation processes, where we have already seen that the deformation or the slip process takes place by movement of the dislocation. So, dislocation glide. So, here only the temperature is how it is helping. The dislocation glide is helped by the thermal activation. Okay. So, we want to see that how when a dislocation moves, how the potential energy changes, okay, during the movement from one atomic site to the next atomic site. If you see that if dislocation is here, it is in a low energy configuration. Okay. When the dislocation is moving to the next position, it has to climb over the atom which is in the bottom of this atomic plane. Okay. So, where your half plane is ending, there will be one atom here. Okay. So, if I can show you. So, suppose this is the position of atom, okay, and when it is moving, it has to move from here to this next position. So, this next position is like this. So, basically it has to kind of climb over this bottom atom and go to the next position. Okay. So, this climbing of the atom, okay, is called can be shown as a change in the potential energy. Do not confuse it with the dislocation climb. It is just during the glide process, it has to go over the bottom atom kind, that is the kind of scenario is there. Okay. So, during this process, the potential energy changes like this. It is minimum here, then it goes to the maximum, and then again when you go to the next atomic site, it goes to the minimum potential energy configuration. And this is my obstacle to the dislocation movement. So, E naught is basically, you can call it as activation barrier. So, this much activation energy is required to move a dislocation from one position to the next one. Now, what thermal or temperature does here? Okay, it reduces the, because of the thermal vibration, the atoms vibrate on their mean position. Okay. It kind of gives you additional platform for the atom to go from one position to the next one. So, that extra energy which is given by the temperature is called delta E here. So, you can see my dislocation is already at a higher potential energy here than the next position. So, now it has to climb only barrier which is E naught minus delta E. Okay. So, this is what is helping here for dislocation to move. So, E naught is the activation energy required by dislocation to move from one position to the another, and thermal activation reduces this barrier by delta E. So, if you keep on increasing the temperature, this delta E will keep on increasing and it will become easier for dislocation to move. Okay. So, that was that is already we know that dislocation movement, how dislocation movement gives you deformation. Now, the second one is the creep through diffusional mechanism. Okay. So, diffusional flow creep mechanism. In this there are a couple of mechanisms are there. So, first is neighbor hearing creep, or we also call it as NH. Okay. And this is applicable at high temperature and lower stresses. Okay. So, how high temperature is helping here? We already know at high temperature you will have more equilibrium vacancy concentration, and because this is a diffusional flow, that means you will need vacancies for diffusion of atoms. So, this is going to be applicable at high temperature and lower stress. So, lower stress means I am not applying enough stress for dislocation to move. Okay. So, for movement of dislocation I need certain stresses, shear stresses. So, if I am keeping the stresses low, I am not initiating the dislocation movement, okay, and I will be relying more on diffusion processes. So, in never hearing creep, the diffusion is only through within the grains. Okay. So, it is only going to be lattice diffusion. So, the mechanism is like this. Suppose you consider this as a one grain, a kind of a cube here, only one side is shown here, and the stress is applied in this direction, tensile stress. So, what will happen if I am applying a tensile stress in this direction? I am kind of creating more space for atom by applying a tensile stress. Okay. So, what will happen? The atoms would like to go into the side where the tensile stresses are there, and these are the induced compressive stresses because of the tensile stresses. So, I am trying to compress something. Okay. So, atoms are getting compressed in this direction, and I am applying a tensile stress in this direction. So, I am opening spaces here, kind of I am stretching the bonds here. So, what will happen? The atoms will have a natural tendency to move from compressive side to the tensile side. Okay. They will get more space there for to accommodate atoms. Okay. And vacancies will move in opposite direction to this mass flow. So, basically because vacancies are moving like this, atoms are going to move like that. Okay. And how vacancies are there? Because we are doing this particular deformation at very high temperature. So, high vacancy concentration will be there. Okay. So, mass flow will takes place from compressive side to tensile side, and the vacancy flux will be moving from tensile side to compressive side. Okay. So, overall you will see that the material is getting stretched in the tensile direction because atoms are coming from compressive side and getting deposited kind of in the tensile side. So, your elongation is there. So, the original shape is shown here in the red color, and after deformation it will be elongated in the tensile direction. Okay. And getting or cross sectional area is reducing in the compressive side. Okay. So, that is what is written here: atom mass flow from compressive side to tensile side, vacancy flux flow from tensile side to compressive side. Okay. And diffusion of atom leads to change in the shape. So, that is this is NH creep, which depends on the diffusion through the grain. So, it is dominated by lattice diffusion. So, it is obvious that if you kind of want to find out the activation energy for this diffusion, it will be equal to the self diffusion of atom. Okay. Now, diffusional flow creep mechanism, another key creep mechanism is called Coble creep. Okay. And in this case the diffusion along grain boundaries is important. So, diffusion is not through within the grain, but the diffusion is taking place from the grain boundary in a polycrystalline material. Our diffusional area will be equal to the width of the grain boundary and what is the size of the grain. Okay. So, Coble creep is more sensitive to grain size than NH creep. So, you can understand that because the mass flow is through grain boundary. So, if I keep on reducing the grain size, I will have more grain boundary area. So, the Coble creep will start dominating it for finer grain materials. Okay. So, Coble creep will dominate in fine grain material because you will have more grain boundary area as compared to a coarse grain material. So, in coarse grain material you will have NH creep, and fine grain material you will have Coble creep. Okay. In general, both the creep processes operate in parallel. Okay. So, anyone can dominate depending upon the grain size. Okay. So, coarse grain material NH creep dominates, in fine grain material the Coble creep dominates. Okay. And that is how the deformation process is there. So, in this direction you are having the tensile stresses. Okay. So, the vacancies are flowing towards the compressive side and the atoms will flow in the tensile side. In case of Coble creep, okay, the diffusion of atom is taking place through the grain boundary. Okay. So, the atoms are moving through the grain boundary towards the tensile side, and that is how the deformation is taking place. So, we can express all the creep kind of phenomena through a phenomenological constitutive equation, okay, which gives an equation like this. So, epsilon dot SS is equal to, there are a lot of parameters are here, but you do not get scared by this equation. These are not very difficult equation to understand, okay. As we just discussed that my creep phenomena depends on the grain size. So, for coarse grain you will have NH creep, for fine grain you will have Coble creep, okay. So, there is a grain size dependent parameter is here, okay. So, D is your grain size, okay, and B is your Burgers vector. So, it is all these values are kind of normalized with some constant, and you have an exponent here. So, this is a grain size exponent, okay. Now, here is your some stress sigma, which is acting on the system, that is normalized by the shear modulus G, and again there is a constant for that, which will be called as stress exponent. Then here A is a constant depending upon the material and deformation condition. D is your diffusion coefficient, which is given by an equation like this, already we have seen this. G, I just told you, is shear modulus or modulus of rigidity. B is Burgers vector, K is Boltzmann constant, and T the temperature of the deformation, okay. So, this is these are all the parameters here, and depending upon the deformation mechanism, the values of these parameters are given here, okay. For NH creep, it is favored at high temperature, low stress and larger grain size. Description, it is vacancy diffusion through crystal lattice, okay. A will be in this range, N is equal to 1, okay, and P, that is the grain exponent, is equal to 2. For Coble creep, it is favored at low stress, fine grain size and temperature less than those for which NH creep dominates. So, this is at a lower temperature, okay, where the diffusion through grain boundary will be dominating, okay. Vacancy diffusion along grain boundaries, A will be in this range, okay. N is again 1 here and P is 3. So, you can see that in Coble creep the grain size is the dominant, and that is why you have a higher value of exponent here. Grain boundary sliding, okay, favored same range as NH and Coble creep, sliding accommodated by vacancy diffusion through the crystal lattice, okay. In this case the N is equal to 2 and P is 2 or 3, okay. So, 2 at coarse grain material, for coarse grain material, 3 for fine grain material. Dislocation creep is applicable at high stress, lower temperature in comparison to Coble creep and NH creep. Dislocation motion with climb over microstructural obstacles, okay. N is around 3 to 8 and P is 0. So, there is no grain size dependence in case of dislocation creep, okay, whereas there is a high stress dependence on the in case of dislocation creep, whereas in case of diffusional creep there is a stress dependence is very small, okay. So, stress is not a very important parameter, whereas in dislocation creep there is a large stress dependence, okay. We can actually divide all these different mechanisms on a deformation mechanism maps. So, very convenient way to see that in which zone which kind of deformation mechanism or creep mechanism are going to dominate. So, this is a graphical way of representing dominant deformation mechanism at a particular stress temperature combination, can be used to estimate creep rate, okay. So, you can see on the x axis we have plotted T upon T melting point. So, this is the melting point of that material, and when you express something like this, this is called homologous temperature. Okay, any temperature divided by the melting point of that temperature. On the x axis you have a stress which is normalized by the modulus of rigidity, or in case shear stress also you can express in terms of shear stress. Okay. So, this is your ideal shear strength of the material, okay, which we have calculated theoretical shear strength. Below that you will have a dislocation glide mechanism. Okay. Now, we can start seeing that at high temperature we just said that NH creep will be dominating. So, it is diffusion through lattice, NH creep will dominate at high temperature, lower stresses. Okay. So, lower stresses and higher temperatures. Coble creep will dominate at again higher temperatures, okay, little bit more stress than the Coble creep. Dislocation creep will dominate at higher stresses and lower temperature. So, at high temperature also it will be dominating, but it will go towards the lower temperature also. Okay. So, at higher stresses and lower temperature you will have dislocation creep. Okay. Only when you reduce the stress at high temperature the NH creep will start dominating. So, if you see here as I am reducing the stress at the same temperature instead of dislocation creep I am started having diffusional creep. Okay. So, this is the whole different mechanisms can be shown for a particular material in a simple map like this, okay, to kind of find out that if in my material is going to be exposed to this temperature and it is going to be loaded by this much stress, okay, what type of deformation mechanisms are going to dominate, that we can find out. So, once I know that it will be dominated by dislocation creep, then I will design my material or microstructure according to that requirement. If I find out that it will be dominated by diffusional mechanism, okay, then I will design my material or tailor my microstructure according to that requirement. So, this will give me an idea that what material to be used. Okay. Maybe I can go to for the another type of material which will have for which this diffusion this creep mechanisms are shifted to higher temperature. So, my material is going to be safe at that particular temperature. Okay. For example, if I find out that my material is going to be exposed to this stress and this temperature. Okay. So, maybe I can choose another material for which all these mechanisms are going toward the high temperature. So, my operating the service conditions are still within the elastic regime. Superalloys are one of the example where the creep ideas or the ideas from creep deformations are used, okay, or the understanding of the creep mechanisms are used. Okay. So, usually these superalloys are either nickel based, cobalt based or iron based superalloys are available. In nickel based superalloys, for example, the gamma prime coherent precipitate, which is shown here by these cuboids, okay, these cubes kind of nice arrangement of precipitate is there. So, this gamma prime coherent precipitate, which is consisted of nickel 3, either aluminum is there or nickel 3 titanium is there. In nickel FCC matrix provide particle strengthening and creep resistance. Okay. So, basically it provides an obstacle to dislocation movement. Okay. So, this kind of material can be used at a higher stress condition and lower temperatures, okay, because it will be able to give a effective obstacle to the dislocation movement. So, wherever dislocation creep is dominant, we can use a material like superalloy. Okay. So, we can also estimate the creep life. Okay, and one of the ways of estimating creep life is through a parameter called Larson-Miller parameter. Okay. So, basically the idea is like this, we want to find out that what is the time to rupture, okay, and it will depend on stress and temperature. So, you can see on x axis we have plotted 1 by T here, and on y axis we have plotted log of rupture time. So, rupture times are in 2-3 order of magnitude will be there, okay, that is why it is plotted on log scale here. So, for example, if I do a testing at stress sigma 1, okay, so this will be how this is how the curve will come between the 1 by T and log TR, if I do another test for the same material at another stress level, you will get another curve. So, for each stress condition you will get one curve here. Okay. So, it is kind of difficult to get so many curves and kind of find out a life of the component under creep condition. Okay. So, for example, if I am using this particular material at a condition where the stresses are going to be sigma 1. Okay. So, this is the temperature and I am using my material at a condition where the sigma 1 stresses are applicable on that, then this will be the time to rupture. So, that will be my creep life. For the same temperature, if I am using the same material at a stress which is sigma 2, okay, then I will be having the rupture life as this one. Okay. So, this is one life, this is another life, you can call it TR1, TR2 let us say, and TR1. So, from here I can tell you that the sigma 1 is more than sigma 2 here, okay, because my time to rupture is reducing as a function of stress. So, sigma 1 is more than sigma 2. If you have even lower sigma value, the creep life will increase. Okay. Or if I change the temperature, suppose for the same stress cycle, if I reduce the temperature, if 1 by T is increasing here, the temperature I am reducing in this direction. So, if I reduce the temperature, you can again see that my creep life has increased. Okay. So, reduction in stress and reduction in temperature is going to increase your creep life, okay, in general. So, I can express all this data for each of these stress different stress acting on the system by a Larsen-Miller parameter. So, this is what is plotted here for a certain alloy, okay, that T is log TR plus 17. So, this has some range for different material, you will have different constant here. Okay. So, for this material the constant is 17. Okay. So, now all the stresses are different stress data is plotted on one single curve here now at different temperatures. Okay. So, on x axis you have this Larsen-Miller parameter which is dependent on temperature. This is the creep life TR, time to rupture, and some constant is there. Okay. So, now if I know that my material is going to be exposed to this stress, for example 200. Okay. So, let us say it is going to be exposed to 200. Okay. Then I can find out that what will be the Larsen-Miller parameter at that stress. So, let us say it is going to be around if this is 20,000, it must be around 19,000 or 19,500. So, here it will be 19,500. Okay. Temperature, we know that for which temperature I am doing the test. Okay. So, that temperature will come here. So, I can find out for this temperature and this Larsen-Miller parameter that what will be the time to rupture or what will be the creep life. Okay. So, now if you want to if you think that this is not suitable, okay, maybe I can try to redesign the my component and bring down the stress to some other level. Okay, and again I can find out that what will be the time to rupture, okay, for a particular condition. Okay. So, all the temperatures curve are plotted on one single curve here. Okay. You can see for different temperatures all are falling in one single curve. So, once I know the stress, I can and the temperature on which I have to use this material, I can find out that what will be the time to rupture. So, either I will manipulate the temperature or I will manipulate the stress to get more life out of the component, or I can use a different material for which you will have again a new curve, okay, and that can be used to have a higher creep life, okay, under the given stress and temperature condition. Okay. So, we can also do this quantification of the creep life, okay, and find out that which material or which service conditions will be appropriate for my component. Okay. So, with that thank you, and so this is our lecture on creep. So, hopefully we have covered the whole idea related to creep and for in this particular lecture. Thank you.